Today we're going to go over rivers, which is topic 9. We just watched this video, a couple minutes long, from the beach, A River of Sand. So this is the beginning of the discussions of the hydrosphere, which is water on Earth. So 97.2% of the water on Earth is in the oceans. And then a little bit more than 2% of all the water on Earth is stuck in glaciers as glacial ice. And then 0.65% of all water on Earth is in the atmosphere, groundwater, lakes, swamps, bogs, and rivers. And this is a model of the hydrologic cycle. And you have evaporation, precipitation, and runoff. So runoff is the surface flow of water, and that's going to be in your streams and rivers. Streams and rivers are pretty much interchangeable words. Rivers are usually a little bit bigger than streams, but not necessarily. Like the Mississippi River, we call it a river. We don't call it the Mississippi Stream. But like if you're in the mountains and you see like a little stream, that's a stream. Okay, so what is runoff? Runoff is precipitation that does not immediately evaporate, freeze, or sink into the ground. And it flows down slope along the surface of the earth. If enough water flows over a particular spot on the land over a period of time, it'll start cutting down into the land. That's called down cutting. Down cutting happens especially where rocks are less resistant to erosion or where there are fractures in the bedrock. So this is an example. This was a little field, and the soil was very rich in clay. So it's kind of like a dry, orange looking soil. This was in Virginia. And there was a little bit of a hill in part of the field. And you could see water had poured down that hill. And over time, you know, like anytime it rains, right? The water would flow down this hill and it would keep going in the same spot, because once you have a little bit of a cut in the land, a little bit of an area where it's a little lower, then the rainwater is going to prefer to flow there. So over time, the rainwater carves out a path in the ground. It carves like a little channel. So although this is not a stream, this was just a really small area of a little hill, it models and it represents what I'm talking about pretty well. So on a larger scale, this is what would lead to the formation of a stream channel. Just water flowing over land and then finding its path and then keep cutting down and down into that path over time. And this is what the land looked like from a little bit further away. Okay, so it's a little tiny bit of this little hill here. So that's pretty much how rivers start out. You have some sort of elevation in the land, and then runoff just cuts down into the land. And that's called down cutting. So surface water moves from high areas to lower areas because of gravity. So it always flows downhill. And we could call running water streams, creeks, brooks, rivers. Rivers are really good at causing erosion. They're very effective at erosion. And they could pick up a lot of sediment and transport a lot of sediment, and then they end up depositing a lot of sediment. So like the Mississippi River, at the end of the river, there's a lot of sediment and that is deposited in the Mississippi River Delta. So where do rivers get their water? They get water from further upstream, from precipitation or from snowmelt, and they also get a contribution from groundwater if the stream channel is deep enough that it reaches the groundwater, then it's replenished by water that's underground. Rivers that only get water from upstream sources can actually dry up when there is no rain. So if they don't have a groundwater input and they're only getting water from precipitation or snowmelt, they could actually dry up. So here's like the anatomy of a river. The beginning of the river is called the head of the river, and that's going to be located up in the mountainous area. And again, the source of the water is from melting snow, groundwater, and precipitation. And usually you don't have a large river channel at the beginning. You have a lot of small tributaries, which are like little streams. They're coming from all different areas within that mountainous region. And all those little tiny streams eventually feed into one main river. But that's going to be a little bit further downstream. So you see where it says numbers 1, 2, and 3. It's just little streams feeding in. And then by the time you get to number 4, you have more of a significant main stream. The end of the river is called the mouth of the river. And that's going to be in a flat area. And the river will feed into an ocean or a lake. Occasionally, rivers will end on flat land as well. We will talk about that later. So here are the 3 zones of a river related to sedimentary processes. So at the head of the river in the mountains, that's where the rivers and the tributaries are producing sediment, and that's through erosion and weathering. See, I added the word weathering. It's not as visible, but see erosion and then it says and weathering. Okay, so that's where all the tributaries, the streams are running over the rocks and breaking apart the rocks over many years. Like the guy said in the video I just showed, he said thousands of years. So you're producing the sediment through weathering and erosion. And then you have the middle part of the stream, which is where the sediment is transported. So that's your zone of transportation. And then at the end of the river is where the sediment gets deposited or left behind. So how do rivers erode land? Most erosion occurs during floods when rivers contain more water and thus more energy to move sediments. You have different terms. Scouring, that's when running water removes loose sediment fragments from the land it flows over. Abrasion is when sediments carried by running water grind against the river channel wall and floors, acts like sandpaper, and smooths out rocks on the stream bed and the channel walls. Dissolution is when soluble minerals become dissolved in river water and are carried downstream as ions. The constant flow of river water over rocks in the river shapes the rocks. It causes them to become oval and flat with smooth, rounded edges. So you get some people in like the decorating industry call these river rocks, or like the construction industry, they call these river rocks. So they're going to be flat and oval and smooth. Then you have an erosional feature called a pothole, and this is caused by abrasion. So you get pebbles or sand get caught in little swirls in the water, and then the sediment rotates and rotates and rotates in that little whirlpool swirl of water, which we call an eddy. And over time, the sediment, like the pebbles or the sand, will grind a hole in the rock because of abrasion. So then over time, you get these holes in the rocks. So in this photo, the potholes, there's a couple on the bottom too here. The potholes are exposed and visible in this photo, but typically they form when the river water is at a higher level, like during a flood. So how are sediments transported in rivers? So in this photo, this river is pretty muddy looking, and that's because it has a lot of sediment suspended in the water. So sediments are transported in rivers in solution as dissolved ions, and that comes from the chemical weathering of rocks. In suspension, which means that you have small particles suspended in the water by turbulent water. So those are going to be silt and clay particles that like remain suspended in the water. Silt and clay is basically what is in mud. And then you have what's called bedload. Bedload is sediments transported along the stream bed. That's mostly sand and gravel will be the bedload. So saltation is when the little sand particles bounce and skip along the bottom. And then traction is more when like gravel rolls and slides along the bed. So then I have an animation. Open that up. Wait, it's not loading, hold on.
Sediment transport by streams. As the river current flows from left to right, notice that the sediment particles move in 3 different ways. The largest particles roll or slide along the stream bed in discontinuous movements. The smallest particles are completely suspended in the water and move with the current without touching the stream bed. Particles of intermediate size bounce along the stream bed. In most energetic streams, the large rolling and sliding grains are gravel, the bouncing grains are sand, and the suspended grains are silt and clay, not visible in the water, but still important to remember, are the abundant ions and chemical compounds dissolved in the water. Watch the 3 different types of sediment transport motion: sliding and rolling on the bed, bouncing along the bed, and suspended above the bed. Bed load describes the sediment grains that spend most of the time on or near the bed. These are the sliding, rolling, and bouncing grains of gravel and sand. Suspended load is the fine-grained silt and clay particles that move within the stream current and rarely, if ever, settle to the stream bed. Dissolved load describes the ions and compounds dissolved within the water.
Okay, so then we have river sediments. And this is a graph that shows you the size of particles compared to the stream velocity needed to carry that size particle. So if you look, the side says boulders, cobbles, pebbles, sand, silt, clay. That's your particle diameter is on the left. That goes along with the words I just read. And then your stream velocity increases as you go to the right on your x-axis. So the way that you read this is as a stream moves faster and faster and faster, you're able to, the water is able to pick up and move larger and larger particles. So if the stream is moving 10 centimeters per second, then it could pick up particles that are 0.2 centimeters in diameter. But if the river moved slower than that, it would not be able to pick up that size particle. So the summary here is that fast water can move larger sediments, slow water can move finer sediments. That's the summary here. Okay, and then this is a diagram that's in your book. It's pretty much the same thing. Okay. And then this is a picture that is related to what we're talking about. So you have this river, and this was either in upstate New York or Vermont. I don't really remember. But you see all these really large rocks sitting in the river, but it also looks like there's not that much water in the river, and it looks like it's not, I mean, over here it looks like it's moving a little bit fast, but if you look in the background, there's not really even that much water in the river. So then the question would be, like, how did these humongous boulders get here? Right? How did all these large rocks get moved? But then you see evidence at the stream bank, and this is where you see like the soil got kind of ripped up and there's tree roots sticking out. That shows you that the river water at some point probably was at that height. So at some point there was more water in the river during a flood. Now, we don't know when the flood happened just by looking at this, but at some point, the water has been higher in this river. So now what we can do is, and if you don't have this printed, you could just draw this little stream profile on a piece of paper. So this is a stream profile, or the side view of a stream going downhill. So we can draw in the sediment grains as they would be deposited at the end of a river. So if we go back to this, or again, it's the same thing. As a river increases in speed, it is able to pick up certain larger particles. But then as a river slows down, it drops those particles in the same order, but backwards. So as a river speeds up, it could pick up clay, then silt, sand, pebbles, cobbles, boulders. But as a river slows down, it's gonna drop those boulders first, then it's gonna drop the cobbles, then it'll drop the pebbles, sand, silt, and clay usually is pretty much, if the water's moving at all, it'll probably have some clay moving in it. Okay, so as the river slows down, the first particles to fall are going to be the largest particles. Okay, so as the river flows into a lake, it slows down. So what's the first size it's going to drop? You could write the answer in the chat. What is the first size that's going to drop as this river slows down? Correct, it's going to drop the boulders first. So where you would draw like right here, some boulders. If you don't want to draw it, you could just write the word boulders. Yes, that is correct. So the boulders, and then you would write out the other words, or you could draw them. What would come after the boulders? Right, pebbles. Okay, so go ahead, take a minute and sketch that out. So that the boulders fall first, and then pebbles, and then sand, silt, and then clay would be like all the way out here. Okay, so then when you look at this pretty much is the answer. So large particles fall out of the water first as the river enters either this is a sea or a lake, and that's because the water is slowing down. So it drops the largest particles first, the boulders and then the pebbles, sand, silt, and then clay would be like all the way out here. So the next thing is to discuss the energy of a river and what controls the energy. So rivers have more energy when they flow over steep land than when they flow over gentle land. So the steepness of the land is calculated as gradient. It's like a rise over run. If you ever did that in class before, science class or a math class, you may have discussed rise over run. So that's the steepness of the land. So steep gradient rivers erode the land downward into the land, called downcutting, and that creates canyons and a steep V-shaped river valley. So that your higher gradient is in the mountains in the head of the river, and then the mouth of the river is generally flatter or lower gradients. So this is the calculation for gradient. It's the change in elevation divided by the distance, which is the length of the stream. So rivers that flow over steep land erode land by cutting downward. The valleys are formed in a V shape as unstable pieces of the valley walls fall off due to gravity as supporting pieces of rock below them are eroded by the river. So if it were not for the pieces falling off the valley walls, the valley would be more vertical, like the blue box to the left. This blue box here would be more the shape of a river valley if we did not have pieces falling off of the valley walls after the base of the valley walls is eroded. So that's why it becomes like a V shape instead of a vertical canyon. In some cases where we're gonna find a very steep canyon though. So here is the evolution of a river. Right, so you have the down cutting in the mountainous area, and then eventually when the river has cut the land downward to be more flat, then the river starts to curve and then it erodes the land outward. So first you get down cutting and the land is eroded downward, and then the land is cut outward, sideways by the curvy river. And that's when you develop floodplains. Now, base level is what we call the elevation to which the river will erode downward until it's flat, until the river is flowing on relatively flat land. Okay, so base level is just the elevation of a river when it becomes flat and can no longer erode downward. Okay, so this is a stream profile. And in this case, the river is not flat, so it could still cut downward. Now, ultimate base level is sea level. So if the river flows into the ocean, the river cannot erode land down below sea level. It would only be able to cut down to sea level because that's the end of the river. Otherwise, a river would flow uphill from the ocean upstream, and rivers can't do that. So ultimate base level is the sea level. So base level, we could also say, is the elevation at the mouth of the river. So sometimes the mouth of a river is just a lake, which at that case would not be sea level. And sometimes it's just another stream, like if a stream is a tributary that flows into another stream. So rivers that flow over gently sloping land have low potential energy and only erode the land outward. And then they're gonna start curving and have wide floodplains. So floodplains are the flat areas next to the river channel. So if you look, the river channel is like the blue curvy line, and then all the flat land next to the river channel is the floodplain. So this whole thing is a floodplain. But then during a flood, the floodplain land will easily get flooded. Okay, and this just shows you the evolution of a river as it erodes downward, forming V-shaped valleys. It reaches base level and starts cutting outward and curving and then developing a well-developed floodplain. Okay, so then we have what's going on inside the river channel. The part of the river valley occupied by water is the river channel. So this is not referring to the whole entire valley with the floodplains and everything. This is only where the actual water of the river is. So within a straight river channel, water flows the fastest where there is the least amount of friction. So here's a segment of a straight river channel, and the dark blue is showing the maximum velocity of the river water. And it's a little tiny bit below the surface because air will cause friction. So it's a little below the surface, and then all like the walls and the floor of the channel will cause friction as well. So the maximum velocity is the furthest away from the channel walls and riverbed. So then we have meandering streams. So meanders are broadly looping curves in channels that flow over gently sloping land. And if you were to go down the river, when you go around the curve, it's kind of like going around a roller coaster, where when you go around the curve in a roller coaster, you kind of feel yourself being pushed to the outside. The same thing if someone is driving a car and you're in the car as a passenger, and if they go quickly around a curve, you'll kind of get pushed to the door. You get like pushed against the side of the car. So in this case, the water is flowing down the stream. The water is going to get pushed to the edge, pushed to the side of the curve. And when it gets pushed, that's where it's going to erode more. And then the opposite side of the curve is where it's going to just deposit sediment, because that's where it's slower. Okay, and then you keep flowing. And then here you have the water gets pushed to the outside of the curve. That's where it's moving the fastest. So you have erosion on the outside of the curve, and then the inside of that curve is where the water is moving the slowest. So you're going to have deposition. So the erosion is going to cause cut banks to form. That's where the river channel is deeper. And let me just zoom in here. You could see that on the inside of the bend, the inside of the meander, material is deposited because the water is moving so slowly, it can't carry that sediment. So it deposits it. And that deposition is in the form of what we call a point bar. So it's like a section of gravel and sand, for example. And then if this erosion and deposition continues, you will form something called an oxbow lake, where a meander gets cut off from the rest of the stream. And this is just another diagram showing you where the maximum velocity of a meandering stream channel is. So it's on the outside of the bend is where the fastest water is moving. So here you have a straight channel where the fastest water moves in the middle, and then a curved channel, the fastest water is on the edge. And then you have this picture on the side that shows you this house. This house was not built on like the edge of a river, like half into like nothingness here, right? So when they built this house, there was land underneath the whole house. But over time, you got erosion on the edge of the bend, as you can see down here. So over time, the river cut into the land on the riverbank. And now this house is kind of just like hanging off the side over part of the river. But it wasn't built in that spot. It's just that the river cut into the land over time, and now they have a problem. Sinuosity is just how curvy is the river channel. So low sinuosity is going to be a straight river channel. High sinuosity is a curvy river. Steep rivers with a straight river channel are usually a mountainous region, have steep valley walls, have a V-shaped valley, and the erosion deepens the river valley. And then the gently sloping rivers tend to have a meandering channel. They have gentle, wide valleys with wide floodplains. Highly sinuous rivers are also going to erode the land outward and widen the valley, and oxbow lakes may form. Don't worry, we're not going to do the math here. I just put the formula there, but we're not going to work on that. Oh. Okay, so now I have this again. You do not want to buy a home on or near the outside of a river bend. That is how that works because of the erosion. Okay, so then I have this animation. This shows you stream processes like the formation of oxbow lakes and the formation of floodplains.
Meandering stream processes. The opening screen of the animation shows a curvy, meandering stream flowing in a valley. Meandering streams get their name because they wander back and forth across the valley. The horizontal shifting of the channel also widens the valley over time to produce a floodplain. Look carefully at the labeled features when the animation stops. The water velocity is fastest around the outside of the river bends and is slowest on the inside of the bends. These velocity differences mean that erosion happens along the outside of the bend, producing the cut bank, while sediment deposition forms a point bar on the inside of the bend. The meandering channel shifts across the floodplain because of this simultaneous erosion and deposition on opposite sides of the bends. A meander scar marks the former position of the channel cut bank on the floodplain. In some cases, looping segments of the former channel remain as distinctively shaped oxbow lakes. Notice the positions of the eroded cut banks on the outside bends of the stream and the point bar deposits on the inside bends. Erosion of nearby river cut banks cuts off a loop of the channel to form an oxbow lake. The lake may eventually fill with sediment and remain as a meander scar.
Okay, and then here's a photo of some point bars. And if you look in the background, there's some more. So you have this one, which is right near where I was. I was on a bridge, I was not in the stream. But here's a point bar that is on the inside of the bend where the water slowed down and deposited all this gravel. And then in the backgrounds, you have more point bars. So there's less water in the river in late August because it's after the summer, you have, drought. We have less rain in July in the Northeast. So sometimes you end up with a little bit of a drought by the end of the summer. So river water is going to have, the rivers are at a lower level. So that's just point bars. Okay, the Oxbow Lakes we talked about. Here you have, if erosion keeps happening over here and over here and over here, then this neck is going to get cut through by the main channel. So then this river water will just cut through there. It's easier to cut through here than it is to go around this whole bend. So you take the path of least resistance. Usually you cut through these necks during a flood though. Okay, so during a flood, the water is gonna cut over this section right there. And then this loop will get separated from the rest of the stream. So here's just more photos and drawings. Then we have floodplains. Floodplains are low-lying flat areas next to river channels, and during a flood, they are typically going to be underwater. Usually within a floodplain, the sediments are fine-grained and they're going to form nutrient-rich, fertile soil. So a lot of farmland is actually on floodplains. But then the problem with that is if there's a flood, the farm would get flooded because it's on a floodplain. Then we have something called braided streams, and it's called a braided stream because it kind of looks like a hair braid, like it's braided. So this is when you have shallow channels separated by many sand and gravel bars. Braided streams are related to streams, braided streams form when rivers are overloaded with sediments. And commonly braided streams are associated with melting of glacial ice. So the braided streams examples are usually from Alaska or somewhere where there's glacial ice melting. So what happens to the sediments at the end of a river? You form a delta. A delta is a wedge or apron-shaped deposit of sediments at the mouth of a river where it enters into a large body of water. The delta is going to form if the river carries a lot of sediment. Some rivers, like the Hudson River does not carry a lot of sediment. So you're not going to find a delta at the end of the Hudson River. Excuse me. So some rivers end on dry land, and the sediments are then deposited in an alluvial fan, which is like a fan-shaped deposit, but it's on flat land. So here are some examples of deltas. You have the Nile River. That's more of the classic delta shape. It looks like a triangle, which is like the letter delta, the Greek letter delta. Then you have the Mississippi birdfoot shaped delta. Here's another picture of a river delta. This is in Alaska. And you see a braided stream. So that was a discussion of what happens to sediment at the end of a river, but what about the water? So an estuary is when fresh water from the river meets marine ocean water, and then the water becomes diluted salt water. So we call diluted salt water brackish. Now, smaller rivers can feed into larger streams. Those are called tributaries. That's not going to be related to an estuary. So these are like three different situations that could happen to the water at the end of a river. And then another situation is that large rivers can branch off into smaller rivers called distributaries. And that's going to be at a delta or an alluvial fan. So like these streams are distributaries. This is a picture of an alluvial fan. So following a storm in a steep mountainous area, materials that are weathered and eroded in the mountains are transported down slope. And then they're deposited on flat land next to the mountains. So that's an alluvial fan. Then you have stream drainage basins. That's the entire area of land where the surface water ends up into one major river. That's also called a watershed. So drainage basins are separated from each other by a divide, which is like a high part of the land. It's typically going to be a ridge or a mountain range or something. So the continental divide along the Rocky Mountains divides the runoff in the United States, where everything east of the continental divide ends up in the Atlantic or the Gulf of Mexico, and everything west, the water that hits any of the land west of the continental divide ends up in the Pacific. So this is what a divide looks like. We have water going down one side when it rains and then the other side when it rains. So then this whole thing here is your watershed. Here's the continental divide. So this is the Mississippi River drainage basin. And then it shows you broken down into smaller basins. So the upper Mississippi, the Missouri River Basin, the Arkansas red, white. Okay, so this is just showing you an example of different river basins within the Mississippi River drainage basin. So this is an example of a sign that indicates what watershed a particular tributary is part of. So in this case, this was the Wallkill River in New Paltz, which is a little bit upstate New York. It's within the Hudson River estuary watershed, but it's like a little stream where I was at that moment. It was a little stream. It's not like a humongous river at that point. So then there are different drainage patterns that you might get that streams can exhibit, because streams prefer to erode land that is easy to break down, because it, like wherever it's less resistant to being weathered. That could be due to the way the rock types are arranged, or if there's like faults or fractures. So like here's a dendritic drainage. This is a stream network that resembles tree branches. This is the most common drainage pattern. Then you have rectangular drainage. That's going to be where you have joints that are intersecting at right angles. You end up with rectangular drainage. Trellis is when you have two stream channels parallel to one another. Radial is common with volcanoes. And then deranged drainage is when you have poor, irregular drainage patterns, and then you're going to have a lot of swamps and lakes and marshland within this area, which is the least common drainage pattern. That I'm not exactly sure. Maybe rectangular. Rectangular is not extremely common. I don't have like the statistics on that, but that one's probably the less common. Now, deranged is common in areas that were affected by glaciers. So this one you're gonna have in a lot of areas, like anywhere where there was glaciation. You could have this. So what happens is you could have rivers in an area and then the glaciers came and like kind of erase all of the previous river channel patterns. So then you're left with just this kind of irregular pattern. Yes, you could watch the recording later. That's fine if you're having connection problems. Okay, so this, you know, in parts of Canada, for example, you would have patches of deranged drainage because maybe you didn't have enough time elapse since the glaciation to have a new stream pattern develop. Okay, have a good weekend. Okay, so then we're going to talk about floods. And I have this video. I will share it. Whoops.
Rivers in New Jersey cresting tonight again. Heavy rains in a short amount of time, swelling the rivers for the second time in the past 6 weeks. But this time, one town tonight looking for a long-term solution, while another is bracing for another round of flooding. Eyewitness News reporter Lucy Yang in Wayne for us tonight. Lucy.
Bill, the Passaic River is supposed to flow gently behind these homes, not up to the homes, around them and into the front yards, as you see behind me. The river has now crested here in Wayne, which means emergency management officials will be on alert all night to see how much more damage is coming their way. It may look like a tree in a lake, but it's actually in a parking lot. All eyes tonight watching just how much farther the water will inch past its banks here in Wayne.
So to have to go through it month after month, it's kind of hard on everyone.
Over in Pequannock, the flooding is finally receding and residents and fluffy pets are drying out. This marks the third time this year they've been submerged, and now they are demanding answers. They want to know how 3 inches of rain can turn into 5 feet of flooding.
Somebody is opening a floodgate somewhere because 3 inches of rain doesn't do this.
The mayor says they can't keep mopping up like this, so there are 2 long-term solutions on the horizon. First, the state has finally agreed to dredge the swollen river. Problem is, they committed only $350,000 for the job.
Which is nothing as far as we're concerned. They need to put a lot of money into doing this project.
The mayor has also submitted a list of 130 low-lying homes along the river for FEMA to purchase. That may seem like a ticket out, except the value of these homes is far less than homes on higher ground.
What if they give you a dollar amount and it's not enough to buy a house further north?
Then we're gonna have to stay here. They have, you know what I mean? We can't. They have to give you something in order for you to move somewhere else.
Now, to be clear, FEMA has not promised to purchase any of these homes. It's still early in the process, and other towns are vying for the same limited federal dollars. Plus, more bad news. Every time it floods, the market value of these homes drops. We're live in Wayne tonight. Lucy Yang, Channel 7, Eyewitness News.
Okay, so that is from 2011, but it is a really good news report. Now, that's the Passaic River, and there was a long period of time where like every year you would hear in the spring, you would hear about flooding in the Passaic River in in some parts of New Jersey, like Wayne, Patterson, Little Falls. So they definitely had a flooding problem. And you would see in the news, like people going down the street in boats, as you see in the thumbnail on the screen right now. I'm not sure if they dredged or not, but they may have dredged the Passaic at some point. Dredging just means that you remove sediment from the base of the river channel and it leaves more room for water. rather than sediment filling in the channel and then having less water, less room for water. So I don't know if it's a matter of dredging or if they maybe built up like the river banks with levees. I'm not really sure exactly what happened. So what causes floods? When there is too much water for the land to soak up, so then any additional water will run off the land into the rivers, and then that will cause the flood. So there are two types of river floods. You have flash flooding and prolonged flooding. So where we live, sometimes you may get an alert on your phone that says like flash flood warning. I know I've gotten that. I know people whose cars have gotten flooded during a flash flood. Like someone I know, their car got flooded on Hempstead Turnpike. I think they were somewhere near like the Nassau Coliseum. And they got stuck in a flash flood, and they had a very low-lying sports car, very small car. So it got flooded, actually. So flash flooding is when you have a high intense rainfall over a short period of time. So usually that's associated with like a summer thunderstorm. And usually that's related to a small drainage basin. So the rain can't sink into the ground fast enough and it ends up running into the rivers. But if you don't even have rivers, it'll just flow into the street. But there are little streams here and there that, a lot of people don't even realize that are there, like really, really little streams that go behind people's houses and things. And, the people who live there know there's a little stream, but it's not like a huge river, going around. So when you have steep land, the flash flood is going to be worse at the base of the steep land. So prolonged flooding is when the water levels rise gradually over several weeks or days, and the flooding happens in a large drainage basin. That's caused by heavy rain over several days to weeks. The ground is too saturated for any more water to sink in, and then the excess water will run off into the tributaries and then eventually into the main channels. So it takes a while for the prolonged flood to happen, as opposed to flash flooding, which could happen within like a half hour to an hour. Like all of a sudden you have a flash flood. So this is an image of the Iowa River in spring 2008. And the water levels rose slowly and the residents were able to evacuate. During a flash flood, you don't actually have that much time to evacuate. But in this case, people were able to leave. Also, last spring in 2019, you had a significant major flood in the Midwest. So particularly Nebraska and Iowa. At this point, a lot of people may not even remember that this happened, but there was major flooding. So the Missouri River reached record-breaking levels because of the heavy rain, but also you had a situation because it was March, you had a lot of snow melt and ice that was thawing as well. So all of that ends up in the waterways, but also because the ground was frozen and it wasn't able to absorb so much runoff water, the runoff ends up in local streams. So all of that led to major flooding. And you ended up with situations like this, where a tractor trailer was swept off the road by floodwaters. And I have a link to the article if you're interested. Okay, so how do we control floods? You can build dams, levees, floodways, flood walls, and you could dredge streams. So a dam is built to control floodwater. It holds back water if it's too high. And then there's the ability to actually release some water flow. And then also another point of the dam is to create a reservoir behind it. So the reservoir keeps water for drinking and farming and irrigation. So it holds water by forming a man-made lake, which we call a reservoir. A levee is an artificial bank that's constructed next to a riverbank. So basically this like high area right next to this stream is the levee. So they build kind of like this ridge or like a hill, like an elongated hill, more like a ridge next to the riverbank. And then they build it to a height statistically that's going to hold back most streams. The problem is with climate change, we're having worse and worse flooding. So you are going to have the levees are not necessarily tall enough in some areas. Then we have floodways. A floodway is a way of controlling a flood. So before the flooding, the stream water goes through, right? Floodway. And then you have a flood. You put the control, you engage that control dam, and then the excess flow is going to go out to the side down a floodway channel. The floodway channel is just an extra channel that branches off from the main river so that you have excess water going there. It controls the area so that on the other side of this control dam, you don't have a flood. So this is an example of a floodway. So this is just, it's made as a river channel to hold excess water during a flood. Then you have flood walls. So here's a wall built on the bank of the Danube River in Hungary. It's just a wall. That's it. And then dredging. Dredging, I think of like as a vacuum cleaner that sucks sediment out from the bottom of a river channel. Okay, so number one, silt builds up on the riverbed over time. During heavy rain, the river could flood. If you remove that sediment, it increases the capacity of the river channel so that it holds more water rather than this part of the space of the channel being taken up by sediment. Now, more of the channel can be filled in with water. So next time it floods, it may not actually go over the riverbank or over these levees. So dredging is a good thing for controlling floods. Okay, and then we have this video about river pollution. So this video is about the Passaic River. And it's pretty interesting. It goes into the pollution of the river related to the industrialization of America. It's only like 5 minutes, almost 6. And then we're actually done with class for today.
I like the Passaic River because it's abandoned. This is the Passaic River.
By the way, there are a couple of times where you might think like, what? You'll see. It's kind of, they say kind of strange things a couple of times that you might be like, what is happening?
This is my backyard. Everybody sleeps on this river. There's some nice fish in here.
This river is pretty much ours as rowers.
It's pretty dirty. I row with my mouth closed, just put it that way. I don't want to get splashed.
They'll dump bodies, they'll dump anything in there.
Really?
That's what I mean. They say, yeah, I don't know. I don't know what's happening with that.
Welcome to the most historic place in America that virtually no one in America has ever heard of.
Like any eager reporter, I wanted a river adventure, and for my sins, they gave me one, the Passaic River. It isn't exotic, it isn't foreign. It weaves through my native New Jersey, more an intestine digesting the garbage put in it than the elegant waterway it once was. The trouble started at a picnic 200 years ago. Alexander Hamilton had lunch here at the river's 70-foot waterfall with George Washington and the Marquis de Lafayette.
And I'm sure General Washington was thinking, boy, this is really a beautiful place. And perhaps the Marquis de Lafayette was saying, this is really a nice spread that the general threw out for lunch. But what Colonel Hamilton appears to have been thinking is, this would be a great place for factories. This would be a great place for industry.
Cotton mills, silk mills, locomotive plants sprung up at Patterson. The first guns that could fire more than one shot without being reloaded were first made here. Colt revolvers, but the Colt mill and most other Patterson factories are closed now. Their skeletons remain. A post-industrial playground for my river guide, Wheeler and Tabanez.
Great Falls, that way, this way, Colt Mill. That's a tourist spot. This is my spot.
Wheeler and Tabanez is the Passaic River's modern-day Huck Finn and my urban Sherpa. Instead of a raft, he glides down the river in his canoe called the Nightshade.
It's amazing to think that at one point, people came to work here every day, you know? And now, it's just sitting here, neglected and abandoned, very much like the river herself.
The Passaic was abused. It served as an industrial toilet. After 2 centuries, it's home to a long list of metals and chemicals that only a trained scientist should have to pronounce.
Can I pull out my cheat sheet?
Yeah, you may.
Right. So the marquee pollutant is this form of dioxin, best known by its initials TCDD. The kind of co-stars are mercury and lead, dibenzofurane, anthracene, benzopyrene, chrysene,
There are
chlorantine,
places where you
chlorine,
don't have to have a scientific degree to see what's polluting the river.
Here in Little Falls, New Jersey, we have much different pollution than they have downriver. The last 17 miles of the Passaic River is dioxin pollution. Up here, we have mainly human pollution from human waste. There's been dead bodies going over this falls. There's been people who have died up here. And a lot of times when the falls are flowing heavy, or sometimes when they're flowing low too, the mist coming off of it, you get the distinct smell of human feces.
Despite all that, a few miles down from Little Falls, in the town of Rutherford, I find rowers out on the water. These rowers know just how dirty this river is. And one of them even remembers he contributed to the mess when he worked at a dye house.
And one of my job obligations was to remove the debris from the dye house, the chemicals, the dyes, directly into the Passaic River. Amplify that to all of the other factories that were on the Passaic River. You could imagine the toxic load that the Passaic River is holding at that time. And that was in the mid-60s.
Around that same time, America was fighting the Vietnam War. We dumped millions of gallons of a chemical defoliant on the jungles there. Agent Orange, its byproduct is dioxin, the most deadly man-made chemical.
Yeah, I'm not really sure why there's human feces in the water either. They don't really go into like why, but apparently there's a smell of human feces at some part of the river. Not really sure why that is.
They made Agent Orange on the banks of the lower Passaic River near Newark, and the waste product dioxin was dumped into the river. As a result, the final 17 miles has a special designation by the Environmental Protection Agency. Superfund site.
At the end of the day, what Newark got out of it was a tomb dedicated to containing that dioxin-laden material, almost like North Jersey's version of the pyramids. You know, I've always said half jokingly that archaeologists in 2,000 years will be excavating here to find out why 20th century man built monuments to pollution.
Despite the Superfund cleanup, the city of Newark is trying to revive the lower river for recreation, but my urban Sherpa likes it just the way it is.
This is the sunken, decrepit, decaying boat, which I love so much, and a lot of graffiti, a lot of just urban living. If you come down here enough and you listen to what the river's telling you, she is crying out to be saved. And that's, I think, why people have devoted their lives to it. And I just think it's unfortunate because I don't think they have a chance in hell of ever cleaning this river. You know what I mean?
Wheeler may be right. History probably flows only one way on this river. The Passaic was a useful tool for jump-starting a new country, and now it's a monument to the price we had to pay to do that.
So if you want to watch that again, it's at the link directly to it is at the end of the lecture notes. I gave you the link. Okay, so that is actually it for today. So for attendance, I'm going to download the Zoom report later. If anyone has any questions, let me know. Otherwise, have a good weekend. And next week we'll do glaciers. And then I do groundwater and soils. And then landslides. Okay, so have a good weekend, everyone. If you have any questions, just stay and let me know. Bye, have a good weekend.